We have to wait until exactly 6 o'clock for this. Yeah? Okay, great. Good evening, everyone. Thank you for coming out to the Coastal Studies Institute this evening. My name is Lindsay Dubbs. I work here at the Coastal Studies Institute, where among other things, I co-direct the Outer Banks field site. And that is a fall semester program for UNC Chapel Hill undergraduates, hosted each year here at the Coastal Studies Institute. Welcome to our Science on the Sound series. It is a monthly speaker series held in this room. Hopefully you've come to a few of these speakers. This month we're thrilled that Dr. Laura Harris is here to tell us about her passion for dirty water. Dr. Harris came to the Coastal Studies Institute to do a workshop with the Outer Banks field site students the past 2 days, and she was enthusiastic to also do a public presentation. Next month, the Outer Banks field site students will be presenting their capstone research at the Science on the Sound, and that is December 13th, a Thursday at 2 p.m. here in this room, so I hope that we'll see you back here. Some logistics for tonight before we get started. Please take a moment to silence your phones, and please hold your questions until the end of Dr. Harris's presentation. And I will be passing around the microphone so that we can be sure that our web guests also can hear the questions. Now I'd like to introduce Dr. Harris. She is an associate professor at the University of Maryland Center for Environmental Science, based at the Chesapeake Biological Laboratory. Dr. Harris is an estuarine ecologist who applies field and modeling approaches to address important questions regarding nutrient dynamics, primary production, and ecosystem structure and function in a range of estuarine ecosystems. Dr. Harris especially enjoys working closely with state and regional agencies in both research and advisory capacities, and is committed to community engagement in her work. She is also committed to efforts to educate young people and increase diversity in the geosciences. She received her BS from Smith College and her PhD from the University of Rhode Island, and she served in a postdoctoral position at the Marine Biological Laboratory in Woods Hole prior to joining the faculty of University of Maryland. Please join me in welcoming Dr. Harris.
Oops. Oh, and of course the mic is coming off right now. There we go. Thanks for the introduction, Lindsay. So I really enjoy engaging with the public, and I'm also hopeful that I can do this in a reasonable amount of time so that we can have some discussion. It's very natural for me as an academic to do these kind of PowerPoint discussions. But I commend all of you to coming to these Science on the Sounds, because I know from the public that sometimes sitting through PowerPoint presentations isn't always the best way to have these interactions. So we're going to try to make sure that I really leave time for a lot of question and answers. And I also enjoy that even though this is a public presentation, we still have a higher density of bad kids sitting in the back and a lower density of here. So it kind of is a universal thing wherever you go, isn't it? So one of the reasons that I want to do this work, I'm just going to spend a few minutes, and part of this is for the benefit of the students. We were so busy working that I only got to soapbox with them a little bit about why I do what I do, and I also want the public to know why I do what I do, and the particular type and approach of science that I take to doing this research. My big motivation for being an estuarine ecologist is because we're in an era of very rapid change. And in fact, geologists have given this its own epoch. So this is now an accepted new epoch that we are living in the Anthropocene. So up until a few hundred years ago, most geologists would agree we were in the Holocene, and now it is really widely accepted that things have changed so rapidly on Earth in such a short amount of time as a result of human impacts that even my colleague Darren Perignac, who's at the University of Colorado, and studies real dinosaur bones. And so usually those guys are very conservative about what they'll call a new epoch. Even Darren is in agreement with me that this is the Anthropocene. And that's a big motivating factor, because it means that as someone who has 2 children, who's thinking about how we're adapting to living in this changing world, I have, I think, a duty as a scientist to think and study these questions. I'm also really fortunate in my position as a faculty member at the University of Maryland Center for Environmental Science. Many academic institutions, and I think that from what I've seen of the Coastal Studies Institute, this is an exception what is happening here, but many of my colleagues at academic institutions are very much rewarded for being given grants from places like the National Science Foundation, going out and carrying out experiments, doing basic research, publishing those in scientific journals that are often not accessible to the public, and so on and so forth. And my institution, UMC's, in particular CBL, my lab is the oldest public laboratory on the eastern seaboard, so we have some pretty cool history. And we are actually established in the Maryland legislature as a place that is uniquely positioned to do service in support of research for the Chesapeake Bay. And so as I mentioned to a few of you earlier, I'm definitely carpetbagging coming here. I'm bringing a little bit of my Chesapeake Bay hat. I know that the Chesapeake Bay hat, sometimes we assume that everyone is like the Chesapeake Bay, and we put on our blinders, and so I'm just kind of putting that up front also as a reminder to me to make sure I remind you that that's the perspective that I'm coming from with this work. And some of it may not be directly transferable to your situation, but I think there's always lessons to be learned from looking at one system and then thinking about how those same processes might work somewhere else. So that kind of position that I have at UMC's, which is focused on service, so I do research, I do teaching, and then I do a heck of a lot of advisory work. And that focus on applied research is really something that we're seeing increase amongst our peers, especially in estuarine science and people who study coastal areas where fresh and saltwater mix. And this is some data from a paper that we published a few years ago with some great colleagues, where we just did a search of a database of all the scientific papers published since the 1960s. And we looked at some keywords that were related to management, that were related to modeling, that were related to restoration. And what we found is that applied research, papers on applied research, are all increasing exponentially. And so clearly it's not just me. There's been a change in how academics are really approaching our science, and we are trying very hard to make our work more relevant. And I think that that's incredibly important. So Lindsay mentioned I have this interest in issues related to diversity and inclusion in the geosciences. Unfortunately, of all of the STEM, science, technology, engineering, and math, of all of the STEM fields, the geosciences least represent the communities who we serve. So we have the whitest and the most male membership in our geoscience academics and faculty. And so it's very important to me that I try to work towards changing the needle on that. And in part of my work, which is funded by the National Science Foundation, one of the things that we find is if we look at National Academies members in the sciences and we ask their motivations for why they do science, we can ask them on an individual level, why are you motivated to do science? And we might array their responses on an axis from concern about a particular problem to wonder at the natural environment. And then we might ask you, what kind of tools and products do you want to come from your research? And those responses might range from problem-solving solutions to discovery. So over here is kind of Jacques Cousteau. So he's going out, he's doing discovery, he's very wondrous in the environment, he's very curious. And that type of person is largely white and male. And when we survey people about this other portion of our axes, folks who are worried about the environment, who want to solve problems, those folks tend to come from underrepresented groups. And so one of the problems we see in the sciences for why geosciences in particular are so difficult to change the needle on diversity is that we haven't quite made this bridge between the two approaches and philosophies to science. And so I'm here to kind of especially speak to the students who are in the back of the room to say that luckily the needle is changing on that. And we are starting to make strides to make the point, because it's so urgent because of the Anthropocene, that applied and basic research go hand in hand. And so the real reason that you guys came to hear me was to talk about wastewater. And wastewater is actually a perfect example of this. Some of our earliest work on understanding the impact of wastewater on coastal waters came from John Ryther. This is John Ryther. He was a shellfish biologist, so he's best known for his work on shellfish. But he was a scrappy scientist living on Long Island Sound, trying to find funding to do his work. And one of the things that he was tasked with doing was understanding the effect of duck farms on local water quality in the lagoons of the far reaches of Long Island Sound. And this very applied problem, he was asked by the duck farmers and by the towns, they were having water quality problems, and they asked him, you know, you're this great scientist here, can you help us out? And so he was an applied scientist, and he went out and he found that actually duck waste was a really good explanatory factor in understanding why these lagoons would start blooming with phytoplankton. Microscopic algae would just bloom and bloom and bloom. And he found that that was because this one nutrient, nitrogen, was limiting. And this is now a cornerstone of estuarine biogeochemistry and ecology. So now we understand that in temperate parts of the world, many of the water quality problems that we have are because we've put more nitrogen into the system than it can handle. And that all came from this guy working on duck waste. So, you know, I love this story, and I love the example it sets for us, and it also starts my story out in a really nice way so that I can tell you a little bit about this carpet bagging approach I'm bringing to you all here. In many estuaries of the world, we do have water quality problems that are linked to nitrogen. That may not be your problem here. So I want to make sure that you all know that I'm not coming here to say that that is your problem. But it provides a nice vignette for how we're tracking back the impact of something like wastewater on the environment. And so the students have already seen this. I should have them present this picture. But I just wanted to give you a brief overview of how nitrogen functions in the environment. Most of you probably hear about nitrogen related to fertilizing your plants. You might hear about it in terms of fertilizer for agricultural fields. And recently, for some bizarre reason, Shell gas stations keep saying they have nitrogen-added petrols. So every public talk I get people asking about that. I have no idea why they put nitrogen on the gasoline. But most of the time in kind of what you're doing day to day, you would hear about nitrogen as it relates to fertilizing your plants. And nitrogen is really important for plant growth. It's where proteins and amino acids and rubisco, which is an essential enzyme for photosynthesis, all need nitrogen. So it's not a bad thing. We need nitrogen, but in too much quantities, it can cause problems. So before humans started to impact the environment, the main sources of nitrogen that plants could take up came from lightning strikes and from legumes, like soybeans. Soybeans are a legume, and they can actually take nitrogen gas out of the atmosphere and turn it into a form, nitrate or ammonium, that plants can then use. Since humans have kind of started to manipulate the environment, we have many more sources of nitrogen, and this has caused some problems. I was telling the students that the main historical event that precipitated changes to the nitrogen cycle was World War I and World War II. And that's because in those days we were on a race with Germany to develop ever better weapons. And some scientists in Germany developed something called the Haber-Bosch process. Has anyone heard of the Haber-Bosch process? Yes, the students have. Yay! So this was a really big technological advancement. We learned how to take nitrogen gas out of the atmosphere. Most of the gas in this room is nitrogen. Only a little bit of it is oxygen, and an even smaller amount is carbon dioxide. Most of it is nitrogen gas. And they developed a technique for taking that gas and turning it into anhydrous ammonia. And anhydrous ammonia is used to make bombs. So that was a big historical event that happened in the world wars. And after the wars ended, we had a lot of anhydrous ammonia. So guess what we started to do with all that anhydrous ammonia? We started to grow corn. We started to grow wheat. And this is when what we call the Green Revolution really took off. And so that's what this picture is really denoting, is how we've changed our nitrogen landscape in the watershed by taking that nitrogen out of the atmosphere, turning it into fertilizer for farm fields. The food is then usually transported in large quantities to villages and urban areas where people eat it, and then it comes out in our waste. So most urine is largely ammonium, or urea again. So there's huge sources of nitrogen in our wastewater. We also produce nitrogen by the burning of fossil fuels, and when that gets into the atmosphere, it can move across the landscape, and then it falls out of the sky either during rain events or even as dry deposition. So what has this done? If we have this combination of most coastal waters being limited in nitrogen, and yet we've taken nitrogen and made it much more quantities of it available, most of that eventually ends up in our coastal waters. And what has happened is that in fertilizing our estuaries and coasts, we have caused more production of organic matter to happen. We've basically, just like the cornfield, we add the anhydrous ammonia and we get lots of growth of corn. When we have a lot of nitrogen in runoff from fields or from wastewater inputs, we can grow a lot of phytoplankton or macroalgae. And that's not always a bad thing. Sometimes it can mean that we also grow more fish. So there's some interesting work being done right now in Tampa Bay where we've actually cleaned up the water there, and yet we're having a little bit of a decline in fish population. So there may be actually a negative effect of removing some of the nitrogen. Most of the time, when we add too much nitrogen in a temperate estuary, though, it's a bad thing. And what we get are blooms of phytoplankton, which are microscopic algae. When the algae die, they sink to the bottom, and the bacteria basically go to town, consuming all of those dead phytoplankton and using up all the oxygen in the bottom waters. And that's what my Chesapeake story is like. We have tons of phytoplankton blooms. When they die, they're sinking to the bottom, and the bacteria use up all the oxygen, consuming all of that organic matter. We also get decreased water clarity because of those phytoplankton bloom. There's less light that goes through the water, and that leads to losses of seagrass. And those have impacts on living resources like fish. All right. And so this is kind of our conceptual model of what a eutrophic, an estuary that has had this big fertilization from nitrogen and a lot of production of phytoplankton. This is what that conceptual model looks like. Increases in phytoplankton, die-offs and decay, consumption of oxygen, loss of habitat because the SAV goes away, loss of habitat because the fish can't live in those low dissolved oxygen conditions. Worldwide, we have seen phenomenal increases in hypoxic and eutrophic areas. Typically, you only get this response in systems that have a long sitting time for the water in them, or that have really strong gradients of salt and fresh water, like we have in the Chesapeake Bay. I was in China a few years ago on the Xiamen estuary. It's kind of just across the Taiwan Straits from Hong Kong. Xiamen Bay has some of the highest nitrogen inputs in the world. But we don't see low dissolved oxygen there because Xiamen Bay is kind of like a soda can. It's just so energetic that the water's constantly being mixed up, and all of that mixing means that we're always getting replenishment of dissolved oxygen in the bottom water. So you kind of have to have this mix of really high productivity of the phytoplankton from all the nutrients with physics. There has to be something about the water column that makes it either still or makes it so that there's fresh water on the top and salty water on the bottom that kind of caps it like we have in the Chesapeake Bay. So I'm going to just give you, now you've gotten kind of estuarine ecology 101 and your brains are exhausted already. I'm going to give you a case study of how we think about these concepts in some of our estuaries and where wastewater comes into that picture as a really large source of nitrogen. And fortunately, one of my favorite case studies is work that I did in the Potomac. The Potomac is the largest tributary of the Chesapeake Bay. It's an estuary in its own right. It's over 100 kilometers long. And it's very convenient to talk about policy and management because it sits right here at our nation's capital. So I was lucky in that I used to put in my boat with my students just below this bridge, and we did a lot of monitoring on small boats. And then you'll see that we've done some cruises on our larger 90-foot research vessel as well. So problem definition. Here's finally my carpetbagger map. This is a map of the Chesapeake Bay where, as an estuarine ecologist, we completely ignore the land. It's white, and we're only focused on the water, which are red and yellow and blue. The colors here denote concentrations of dissolved oxygen. And the red color means low dissolved oxygen. In fact, bright red and dark red are oxygen levels that are so low that we don't think animals can live in those environments. And the problem in the Chesapeake Bay is that this pattern of anoxia and hypoxia, those are the terms we use for low dissolved oxygen, starts in May and doesn't let up until September of every year. So this is a huge water quality problem. It didn't always used to be this way. And here's the Potomac, this giant winding tributary. You can see that much of the lower portion of the Potomac have these symptoms. So sometimes it's useful to think about eutrophication, this process of the estuary becoming too high in phytoplankton and nutrients and too low in dissolved oxygen, as a disease. So we can think of the Chesapeake Bay as having a disease of eutrophication. Its symptoms are those low dissolved oxygen values, the loss of seagrass, habitat not being great. And so we definitely want to figure out how we can make this estuary less sick, and that's a ton of the work that I do in that region, is figuring out restoring and healing the Chesapeake Bay. In the Chesapeake Bay, now you can see we're actually thinking about land, because it's important when we are trying to solve these problems to think about the people that are surrounding the bay and the problems that are serving all of those nitrogen loads to the bay. This is the entire watershed for the Chesapeake Bay. It's large. We have portions of New York State, portions of Pennsylvania, West Virginia, Virginia, Maryland, D.C., and a little slice of Delaware that they try to pretend they're not involved in. And in black here, you can see the outline of the Potomac watershed. So the watershed for the Chesapeake Bay as a whole is very, very big. This is the drainage basin where all of the rain that falls in this area eventually makes its way to the Chesapeake. And you can see that the Potomac has a big portion of that land. We've also seen some really dramatic change in the Potomac watershed. These are data, they're historic data dating from 1900. And we have the population estimates broken out by the states in Washington, D.C. And so you can kind of see this growth in Maryland population, the growth in the Virginia population. There's a decline in the population of the city that starts in the 1950s when urban flight started. And West Virginia and Pennsylvania have kind of flatlined. But regardless, overall, if we add these together, there's been a pretty dramatic increase in population numbers. Coincident with those increases in population numbers were water quality problems in the Potomac River itself. And these, again, are some really great historic estimates and data combined for the Potomac River of measurements and estimates of dissolved oxygen in the river itself. So all these data that look messier are the actual measurements, and then the data that look much neater are from a model. But we have some pretty good confidence in these values, and what you'll see is that, beginning in the early 1900s, we started to see a decline in dissolved oxygen in the Potomac, just adjacent to Washington, D.C., and that was largely because we all of a sudden had enough people in Washington, D.C. that we got a big wastewater treatment plant together at the end of the 1800s. And what used to be a problem that was handled on land, so in most of these industrial cities on the East Coast, you would have essentially a cesspool behind your tenement. And we actually employed people with carts and horses to come and take night soil away. So we dealt with liquid waste in cities through cesspools, and then we actually carted solid waste away and onto fields. And around the 1880s and 1890s, there were too many public health problems from this, which you can imagine. Actually, we don't want to imagine, like how horrible. And so they start, as humans do, we found a solution to this, and we developed technology to deal with these at wastewater treatment plants. If you ever have a chance to visit some of these old wastewater treatment plants, which I love to do, they're typically built in the 1880s, 1890s. They're beautiful Victorian structures. They're a little stinky, but really a very fascinating portion of US history, I think. And so what happened was, in DC, right around here, we were putting in that wastewater treatment plant, and we were putting all of our waste into the Potomac. And that was a huge load of organic material to throw in the Potomac. And just like the phytoplankton, when they fall down, the bacteria eat them up and use all the oxygen, the same thing was happening with all of our waste. And we had dramatic declines in oxygen. And really bad water quality problems and odors. And so right around this time period, we started to do what's called primary treatment of our waste, where we were taking the waste and digesting it in the wastewater treatment plant. And so that's what you see here with these slight improvements in dissolved oxygen. And then there was an additional process added to the wastewater treatment plant in the 70s that further improved that. So in Washington, D.C., there was this really wonderful history that we can follow that's often similar at other cities around the United States, and also parallels some important policy changes that happened in the history of water quality and wastewater in the United States. So as I mentioned, in the 1870s, 1880s, those sewers were being built. In Washington, D.C., we started to actually do surveys and collect data in the 1890s. Including water quality surveys of the entire Potomac. And then finally, something really important happened in the 1960s. So I know I'm not supposed to interact with you till the end of my talk, but I do like to ask people, as an environmental scientist, can any of you guess who my favorite president might be?
Nixon.
Nixon. And why would that be?
He created the EPA.
And the Water Quality Act. Now, he did this with, I will say after yesterday, he did this with a Democratic House. So there was, that balance of power actually on the environmental side of management had some really good effects on how we deal with these pollutants. So he established the Water Quality Act and the Environmental Protection Agency and the Clean Water Act, which permits now all of our wastewater treatment plants came from that. And in my region, not long after that, we established something called the Chesapeake Bay Agreement, which was a historic agreement to get all of those states in the same room to try to fix the Chesapeake Bay. And one of the things that came out of that was this. Now, this is the Blue Plains Wastewater Treatment Plant, just south of Washington, D.C. In the United States, it's the largest advanced wastewater treatment plant, and of its kind, it's now one of two. I used to be able to say it was the largest advanced of its kind in the world. It now got tied with someone from Germany, so it's not quite the largest. But this is an incredibly impressive technological advance. This wastewater treatment plant now not only cleans up all that carbon that can go into the Potomac, but it removes phosphorus and it removes nitrogen to nearly indetectable amounts. It's an amazing marvel of engineering. And the people who work here, the civil engineers, I love engineers in general, but civil engineers I really love. They're like the hippies of the engineering world. They just want to save the world. So I feel like we have kindred spirits in common with one another. And this is kind of the history of nitrogen removal at Blue Plains. This is when it first opened, the 1930s, and I actually haven't added on here. In April 2007, which was just before I started my career at CBL, they had a permit modified that lowered their concentrations, and hopefully the students in the back are paying attention to this, to 4.2 milligrams per liter. And today, that is much lower. They're at actually, I think, 1.9 or 2 milligrams per liter, which is pretty much at the limits of technology for what they're dealing with at their wastewater treatment plant. So even though their flow volume and the number of people they're serving has increased tenfold since 1913, they have essentially cleaned up the water. And while we talk a lot about coastal problems and water quality issues, I think sometimes we don't take enough time to just sit back and appreciate what a marvel of technology and problem solving this is. I mean, this is really remarkable. And it's not just nitrogen. We also cleaned up heavy metals. I mean, these wastewater plants used to put phenomenal amounts of extremely toxic heavy metals into our coastal bays and estuaries. Most of these now have removed phosphorus. So we have done a really good job of solving this problem at these wastewater treatment plants. And we can see that reflected in actual data. So you don't have to really pay attention to what most of these mean, but the big thing is to see that most of them are going down. Except for the pink, this is the actual amount of water and wastewater effluent that comes into the plant. That's gone up, but we've had everything else, all those pollutants go down, which is just remarkable to me. So why am I up here doing this science? Problem solved, right? Well, when we're talking about restoring the bay, one thing that happens is that we create models to try to make decisions about how to clean up the bay, and then we need to use science to make sure those guesses that we made in the model worked out okay. And in the Chesapeake Bay, even though wastewater is important, it really pales in comparison to agriculture. So these are all of the nitrogen sources to Chesapeake Bay. And you'll see agriculture, 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 agriculture. And then there's just this one line of wastewater. So if we added all these up, this bar would be way up here. And wastewater actually ends up being fairly small. Septic systems are extremely small in the overall budget for the bay. But I'll tell you, it's a lot easier to solve these problems at the wastewater treatment plant or with septic systems than it is sometimes to change behavior of farmers without effective policy. And so what has happened is we have focused a lot on wastewater treatment plants in the Chesapeake Bay region. And so part of my job advising the state was to help them understand we had seen some very incremental improvements in water quality in some of our rivers. So again, I don't want you guys to worry too much over the details of this. This is essentially total nitrogen coming in from the freshwater portion of the Potomac River. And even though it looks like ziggy, ziggy, zaggy, when we do the statistics on it, we see a very small decrease. And that very small decrease is actually pretty impressive when we translate it into kilograms of nitrogen that have been removed. And so our managers wanted to know, did that improvement come from actual management of the wastewater treatment plant, from these declines in the nitrogen concentration in the wastewater? Or could it have come from the Clean Air Act, which actually has cleaned up how much nitrogen is falling out of the sky on the watershed, because we had put in some clean coal rules that had caused measurable improvements in our streams in West Virginia and Western Maryland. And so how do we answer that question? We wanted to essentially fingerprint the nitrogen in the Potomac River and figure out if it was coming from wastewater, or if it was coming from the atmosphere, or if it was coming from farms. And so that's a big part of the work that I did on the Potomac, and it started with this drawing. This is a cartoon that Walter Boynton drew with me one day. He's a big mentor of mine at CBL. And what we basically did was to break the Potomac into 3 sections, and then to do a checking account balance on the nitrogen in each of those sections. We call that a mass balance. But it's basically thinking about how much nitrogen is coming in, how much is going out, and how much is lost or stored within that portion of the estuary. And so we turned that cartoon, which I think is much more beautiful, into this more boring diagram. And the students will see today, with the students, we focused on doing this kind of work, right? So we started to think about what were all the inputs of nitrogen into our system. In our Potomac project, we also had to think about losses. And the losses here come from harvest of fisheries. They come from the nitrogen being buried. And they come from bacteria that can magically, wonderfully turn some of that nitrogen back into nitrogen gas through a process called denitrification. And then because we were just strivers, we also wanted to think about what was happening in terms of recycling of the nitrogen within the Potomac. So we measured all these things, and then on top of it, we fingerprinted the nitrogen. We thought of ourselves as doing environmental forensics. So instead of wearing high heels in CSI in a fancy lab that doesn't exist, we were wearing our muck boots on a boat trying to source track wastewater. And so we did that. This is the Potomac. Hopefully you recognize it from Walter's cartoon. We had a tidal fresh portion. We had this RET portion. We had the lower estuary where all that low dissolved oxygen happens. We did 3 cruises on our beautiful RV Rachel Carson in the spring, summer, and fall. We measured all kinds of different wonderful things, especially denitrification, which is actually very tricky to measure. I'm happy to talk to you all about it. But measuring rates, how fast something changes, is one of the harder things to do as a scientist, but it's also fun. Denitrification is a word that I love to teach people because it sounds complicated, but it's just this wonderful process, as I mentioned, of magically having nitrogen that was once biologically available turn back into N2 gas that's in this room and is not going to hurt the estuary. So it's an incredibly important process. And then we took cores. This is Cindy Palinkas, and she took these very muddy cores, and we measured burial. And out of that, we did this checking account balance. We looked at what came in, we looked at what came out, and the nice thing about that exercise is you can't lie to yourself. So if you look at what's coming in that you've estimated, and you look at what's coming out that you've estimated, the two should about equal one another, right? Or else you've magically produced nitrogen by accident. And so these graphs, the yellow is telling you where we went wrong. So this is kind of nitrogen that we couldn't account for in our checking account. And these are pretty small. So the first thing to notice is that we did a pretty good job of it. This is the total nitrogen budget that we estimated before Blue Plains advanced and started removing all their nitrogen. And then the bar next to it is what it looked like after it put that amazing technology into place. So we see this dramatic decrease in the amount of nitrogen going into the system. And when we break that up by region, by that tidal fresh, by the RET, and by the LE, we see consistent effects all the way down the estuary, even way down 100 kilometers from Blue Plains. And so that's kind of remarkable that one single management action at the Blue Plains wastewater treatment plant seems to have had an impact all the way down at the mouth of the Chesapeake. And we can also see that from data we take on monthly cruises run by the state, where the concentrations of nitrogen that we measure in the water column, how much nitrogen is in the water, is much higher up closer to Blue Plains than it is all the way down here. And we see a marked difference between those two values before the upgrades at the wastewater treatment plant than after. And then this is where I pretend, put on my high heels and walk like I'm in CSI, and we did the environmental forensics. And what we did was to use isotopes, which I'm happy to talk more about. They're basically looking at the molecular structure of the nitrogen and things that happen to it when it gets put into wastewater. And then we used the organic matter signature, kind of a fingerprint of what all those organic molecules look like to track the nitrogen. And we could see how far down from the Blue Plains treatment plant that wastewater went. And we did that in different seasons. And we coupled it to a model so we could say how much nitrogen had made it to the Chesapeake Bay. And so even though I know I'm running a little bit behind, I'm going to take a moment here to just talk to you about what those numbers mean. This column of numbers here, if we just focus on the first numbers, which is about what we estimated, this is the air, which is big, but these first numbers are what to focus on. You can see that in the winter, we have the most nitrogen coming into the Potomac. And the percent of that amount of nitrogen that is from the wastewater treatment plant in the winter is about 10%. How much of all of that nitrogen makes its way all the way down the Potomac into the Chesapeake Bay? About 20,000. And of that amount that makes its way into the Chesapeake Bay, how much is from Blue Plains? About 3.7%. That changes in the spring, where we get a decline in, that should be an increase, it's 135,000. So there's a really big amount of nitrogen, and there's a big amount of Blue Plains nitrogen that makes its way all the way to the Chesapeake Bay main stem. But then here in the summer and fall, it drops back down again. So we could use these numbers to tell Blue Plains, even after all your upgrades, this is how much is impacting that big red blob in the middle of the Chesapeake Bay. And that has real management implications, and it's actually, contributed to decisions they've made about stormwater management, et cetera. So my final vignette, which I think might be a little bit more interesting to you all here because you don't have these giant wastewater treatment plants, is a story that we've done locally in Calvert County, where I live and where I'm located at the Chesapeake Biological Lab. And this has been done, it's been funded by Maryland Sea Grant, but we've collaborated with Calvert County Health Department and their planners. And they have a big program there to try to improve septic systems with these advanced nitrogen removing technologies. And this is one of those advanced septic systems. It's basically a typical septic system with a septic tank settling chamber and then a leach field, but you also install a secondary tank that's full of wood chips and has a pump. And that secondary tank actually does that magical word, denitrification. And the crew that I work with, Michael Gonsior and Andrew Hayes, we've been called the septic detectives. There was an NPR story that ran a year and a half ago about this work. And what Michael's able to do is this phenomenal chemistry, which is that fingerprinting of the organic matter that's in the septic system. So the way septic systems work is you have waste that comes out of your house. It goes through this settling chamber, and then effluent from that settling chamber goes into your leach or drain field. But even a fully functioning septic system has nitrogen that makes its way into the groundwater. And we know that about 60% of the nitrogen that you produce in your house will make itself to the groundwater, even when that septic system is working perfectly. Those advanced ones can reduce that to 10%. But a traditional septic, and the students worked a lot with these numbers today, a traditional septic like what is pictured here, about 60% of it does. So we have kind of a problem in that we're having homeowners put in traditional septic systems, but they still end up being polluters. And that's how they're designed to work. They're supposed to do that. Attenuation of 40% is still really impressive, but it's something that we have to think about in these coastal areas. And so we did a study where we were surveying streams and seeing if we could fingerprint the septic in the streams. This is our county. My lab is located down here. I live near that black dot. Actually, I sample there all the time for us. This is the main stem of the Chesapeake. And we had all these different sites where we were sampling streams that had differing septic densities. So just a simple map to show you, this kind of shows you what our residential density looks like. This is a site that has less houses that we use as a reference site. So we kind of have paired watersheds. And Katie Martin is the graduate student who's doing this as part of her PhD work. These are the preliminary results from that very fancy organic matter fingerprinting, where using that approach, she was able to identify 148 different possible tracers using that ICP-MS mass spectrometry, super fancy chemistry. In addition to her super fancy chemistry, we've also used some simpler approaches to look at tracers of wastewater like sucralose, which we add to our coffee and which comes out in our waste. And I know Lindsay's working with the students here to look at caffeine. So besides this super fancy stuff, there's also some very difficult to measure constituents that can also be used. And we're developing an approach that uses a combination of all these different tracers. So I'm just going to end by saying that my portion of this, Katie does the fancy chemistry, measuring it in the stream. What we want to be able to do is match the concentrations we see in the stream with estimates of how much nitrogen is coming through the watershed. And I do that through modeling. And with the students today, I actually worked on this particular model, which is a nitrogen loading model, where we estimate how much nitrogen is coming from fertilizer, from wastewater, from atmospheric deposition, and then we talk about ways that it gets attenuated through the watershed and come up with a number that tells us how much nitrogen is making its way to a stream. And we use those data with Calvert County to help recommend where they should be investing their dollars for upgrades to their septic systems. So we actually are giving them real recommendations about what to do. This is a slide from a presentation that I do for our Board of County Commissioners every year. And you can see that there's pretty interesting things that we're talking about, continuing to support educational programs. We have a fall pump out program that we try to get septic homeowners to pump out their septic systems. We want to talk about sewer upgrades with them and these enhanced nitrogen removal septic systems. And these are conversations we have based on the data we get from what I just showed you. So we did this with the students. This is my final slide. I know I'm running late. I had a great time working with everyone here and learning about Nag's Head. I know that some of the issues that you have here have more to do with pathogens, which are more of a risk for human health. And the nitrogen processes function in some ways very differently. So a well-functioning septic system should not be producing a lot of E. coli pollution. It should be safe. But it still produces nitrogen. So those two processes are a little bit different. But we focused on the nitrogen because I carpetbagged it here with my Chesapeake Bay perspective. And we actually got some preliminary results, so yay to the students, where they did actually 3 different implementation of the model. The first, assuming that all the septics in Nag's Head were traditional septics. A second one where we actually had numbers estimating the number of advanced septic systems that you have here, which caused a little bit of a decline in the nitrogen loading. A third estimate where the students came up with a number to estimate potential failure rates, so that caused a little bit of an increase. And then they wanted us to do a final run where we invested, I think it was $100 million in turning every septic system in Nag's Head into an advanced septic system, which clearly reduced the nitrogen loads phenomenally. But we were joking that now none of the children can go to school in Nag's Head. But these are the kind of decisions you all have to make. We have to make them in Calvert County. And we usually balance them with cost-benefits analysis around sewering, cost-benefits analysis about targeting particular watersheds where the water quality problems are the worst, and so that you can get the most bang for your buck when you're thinking holistically about these kinds of results. So I know that I talked too much, and I'll leave it at this, and I am happy to take any questions. Thank you. And we have to remember to use the mic, and that's for the webinar folks and also It helps for any hard of hearing folks too.
Thank you. Dr. Harris, maybe I missed it, but if you could, it wasn't clear to me what % of the nitrogen that's coming down the Potomac is from septic systems versus the Blue Plains.
So
and how does that relate to our problem here on the Outer Banks?
So I was mostly focusing on my story of the Potomac, which is very much wastewater from a wastewater treatment plant. And that is not your problem here. That was a Chesapeake story for sure. So in the Potomac watershed, many of the, if I can go back to a map, I might try to, but around DC, most of those people are on sewers. But then when you start to head south, we get much more rural counties where there are more septic systems. On the tidal Potomac, just the part of the Potomac that has tidal water, there are 17 large wastewater treatment plants. Blue Plains is the big bear in the room, but there are also pretty substantial other ones, like the Alexandria Sanitation Association is pretty big as well. I don't have the exact numbers for septic systems, but I would imagine that it's on the order of, if I'm thinking of the counties, there's about 90,000 people in each of those counties. Hopefully the students can see me doing my cobbler math right now. So I would say that there's probably around 25 to 30,000 septic systems as a guesstimate in the southern portion of the Potomac watershed, but that is just a guess. And it's the way that we did the nitrogen budget was to use, we have a very phenomenal, the model I showed you here is a pretty simple model. And it's nice because we can work with counties and they can play with it because it's just an Excel spreadsheet. The Chesapeake Bay watershed model requires a supercomputer to run. And it has a lot more sophisticated mechanisms about groundwater movement, et cetera. And so for this work, we collaborated with the Chesapeake Bay program to get model output that we used to force the nitrogen budget for the Potomac. And that would have included septics. Wastewater in general for the Potomac is, as you could see, it varies between being at most 19 to 20% of the total amount down to as low as 3.5%. So it's not a huge part of the nitrogen budget in the Potomac, but it has a very big impact locally. We've seen huge water quality improvements in the tidal fresh since Blue Plains upgraded their system. So all this work was tied to ecology we did, looking at the response of living resources and dissolved oxygen and chlorophyll and all of that.
I know how wastewater treatment plants, or I know what they do, but I don't know how it works exactly. What happens to the waste after it's taken out of the water? I'm just curious. I'm sure I could Google it, but.
So wastewater comes into the wastewater treatment plant, and it usually goes through a settling chamber first, where basically you're just using movement of the water in a big, large tank to settle all the solids. So as the effluent is moving through this long tank, all of the solid stuff in it is sinking to the bottom of the tank, and then there's an exit pipe on the other end that just takes the liquid out. That solid stuff on the bottom gets removed periodically as sludge. There's usually sludge sheds at wastewater treatment plants, and that is waste that can sometimes be used in agricultural settings, actually. So sometimes they UV treat it, and sometimes they dispose of it in landfills. It's a huge carbon source. And so then we are left with a liquid. Wastewater treatment plant, they either call it effluent or a liquor. And then those go into these large aeration tanks that mix them very, very rapidly and vigorously. And the reason they're doing that is so that there's enough oxygen for the bacteria to eat up all of the carbon very efficiently. Because we don't want that carbon getting into the river and causing those dissolved oxygen slumps. So once they've done that digestion, and that also helps with all the pathogens. And that's happening to some degree in your well, to a large degree in your septic system as it's moving through those tanks. So it's not that different at that point. Then what happens to that liquor is a lot of times we chlorinate it to make sure all the pathogens are gone, or we UV treat it. And many wastewater treatment plants at that stage will put it into the environment, will discharge it. But Blue Plains then takes that liquor and they nitrify it. So they add another step where they're oxygenating the water and adding special bacteria that changes all the ammonia in the water into nitrate, which is another form of nitrogen. And then they make all of the oxygen disappear, and they add $100 million of methanol every year to add back food for the bacteria to consume the nitrate and turn it back into N2 gas through denitrification. So it's pretty phenomenal. And along the way, they're also removing phosphorus, and they're also removing heavy metals. So there's a lot of other processes happening, but that's kind of, and I'm not an engineer, so if I made a mistake, I'm happy to be corrected in that. But that's my understanding of how the process works.
So we have one question online, and then I will make my way up through the questions from back to the front. Are areas of low elevation in the bay experiencing septic system failures from sea level rise or changes in groundwater elevation? And if so, what symptoms and alternatives are available?
So this is where, you know, it's very important for me to have identified myself as a carpetbagger, because we have, I know you all are going through a lot of those water table challenges right now. And that has been less of a concern in the Chesapeake, although we do have problems related to saltwater intrusion because of sea level rise. And there are projections that some portions of the Chesapeake Bay will be dealing with tens of thousands of septic systems that have saltwater intrusion, which would affect how the bugs work. So bacteria can be very sensitive to their environmental condition, and we don't really want saltwater getting into the leach fields. That wouldn't be great. Saltwater brings with it sulfate, and sulfate just, it's so cool, but it's bad for septic systems. When sulfate comes in, the entire bug bacteria community changes into a completely different community, and you have completely different processes, and so you don't want that in your septic system. It wouldn't work very well at all. So we don't have those specific water table issues as broadly as you all do. What we're mostly dealing with, especially in Calvert County, where there's, we're in this rural environment where houses have grown up since the 90s and the 70s really because of a little bit of commuter traffic, is aging of septic. So my septic recently failed. And when we asked the previous homeowner how long it had been there, it pretty much died right on its 25th birthday. And that's about, you know, it's between 20 and 30 years for most leach fields in our soils. It may be different here, but that's pretty much the lifespan of that. And unfortunately, as we were talking earlier, there's not a lot of policy in place for us to go check on a septic system. So we don't have much jurisdiction in our government to go and say, well, this isn't working and you have to fix it. Instead, what our county is doing is when you improve your home, a lot of times you have to do perk tests and think about changing your septic system. If you sell your home, especially in the critical area, which is right along the coast, then a lot of times you have to upgrade to one of these advanced nitrogen systems. But that's going to be a slow turnover, you know, because our houses aren't selling constantly. We're kind of a slow growth kind of county. So it's different from what you guys are dealing with here. And when a septic system fails, the thing to know is that nitrogen gets worse because you don't get that 40% attenuation. You probably get closer to just 5 or 10 when you have surface runoff from a failed septic. And of course, most critically, you don't get those health benefits. You don't get the cleanup of the water from the E. coli and the viruses and everything else. You're just going to have that raw sewage kind of stewing and sitting, and it can be a really unhealthy situation if it gets into receiving waters. We do have combined sewer overflows that we deal with from the large wastewater treatment plants. So when it rains a lot, they get too much water because we have a combined stormwater sewer in the streets with household sewer. And so in those events, they are allowed by the EPA to discharge directly onto the Chesapeake Bay. And that's where we have most of our public health issues. So as part of my work for Calvert County, I also track Vibrio cases. And this last year it was really bad because we had really bad precipitation events. In Calvert County, we have a lot of watermen in the oyster and the crabbing industries. They're cutting themselves. And we've had people lose limbs, and we've had 2 people die in the last 10 years from Vibrio. So the human health concerns are no joke where I am as well, but the source is more typically the combined sewer outfalls from the wastewater treatment plants than failed septics.
You mentioned all of the policies that were enacted by the federal government over the years. Those of us who are local, just regular citizens who don't know too much about what's going on, but have a sense of what's going on. The state of North Carolina recently had the flooding, and we were impacted by the Gen X down in Wilmington, and then we were impacted by the death of all those pigs that died and the chickens that died, and what was the third thing? There was 3 things that happened. Oh, the coal ash, So I'm thinking we're sitting in a major mess right now in the state. And how does that, how do you guys, now you're from Maryland, but my question is, how, I'm sure you interact with other states, you know, in terms of issues that are coming up and problems. How do you guys present these issues to the legislators and to the people who govern us in an understandable fashion so that they can enact policies that make sense?
So my colleague Michael Gonzior, who has the super exciting chemistry, environmental fingerprinting of the septic, he actually just did testimony to our state legislature to help inform the lawmakers so they had the best science available to make decisions about a septic law that they were considering. And so from my perspective, that's one way that we interact with those policymakers is we serve as an honest broker. I certainly have an interest in cleaning up the Bay and the Chesapeake, but I don't necessarily have a political interest in how that happens. I just kind of want it to happen. And I have science that can help support decision making for that. So one way we do is we actually, in Maryland, we're often called to give testimony to lawmakers who are considering laws and considering policy. The other way that we do it is in the Chesapeake region, we have the Chesapeake Bay program, which has advisory groups that are composed of scientists and stakeholders. And those folks use a combination of the science with good, honest decision making. So I was telling the students that when I give my presentation to the Calvert Board of County Commissioners, every year I am up after the fire chief who's reporting on life and death situations and asking for money. And then I'm up talking about environmental issues. So that's always a big reality check to me that I know the decision makers are having to balance all of those different problems. I would say that in the example you say, you're talking about where there may be an advocacy need and there may be a need by the community to leverage the laws that we have, that the most powerful folks I know of in the Chesapeake region who help us with that are the river keepers. I don't know if you have a river keeper association here, but usually they can actually look at needs for a particular river and advocate in a legal sense. And then we have a foundation, the Chesapeake Bay Foundation, that is an advocacy organization, and the Alliance for the Chesapeake Bay. And those guys are like all lawyers. So sometimes they'll ask us for advice, but they're kind of separate from the scientists. Now, in the case of those situations, you know, if I were a person living on those rivers, I would want to know, well, how much of this stuff got in the water? Where is it going to end up? And what's it going to do to me? Now, those are the kind of questions that a scientist can help with. But actually trying to help figure out how you then get the people who are responsible to fix it up or get the state to help you fix it up, that's where I see the advocacy groups come up. So hopefully you can see the difference there is, you know, you're asking the question, how much, where is it going, is it going to hurt me? Science can help. figuring out who's going to pay, the advocacy groups help.
What are the 3 major challenges that you face in the next 5 to 10 years? And it can't, one response can't be additional funding.
Oh, as a scientist, you mean? Goodness, wow, that's a good question. As a scientist, I would say that one of the things that I worry about the most is that we need to have behavior changes coupled to all of the science that we're seeing. And because it gets awfully depressing to keep reporting on some of the same water quality issues and not really know how best to have people think about innovative ways to make those choices. And so what I see as the biggest challenge in my field is taking natural scientists who are a certain breed of person. You know, as you saw from those graphs, the majority of geoscientists tend to want to go discover and think about wonder and kind of do these experiments. But I think we urgently need people who will be able to put their foot over into the public realm and also to be able to work with social scientists. And social scientists are a completely different kind of scientist and a different philosophy and approach to doing the work. And so when I was actually invited to the National Science Foundation, had a series of workshops all over the country last month called Coastlines and People. And they basically had us do this huge brainstorming activity to figure out where are the basic research needs for the country that the NSF should support. And by and large, I felt like the most compelling ideas coming forward was how do we work with social scientists to find out ways where our work overlaps. So for example, in the city of Baltimore, I have another giant research program, part of it's in Baltimore. And we know that things like open green space can improve the microbiome of people. It can actually improve their health by changing the bacteria in their guts just by having parks, at the same time that those parks can help with stormwater management. So those are the kind of things that we need more information on so that then we can go to the mayor of Baltimore, which we're going to be doing shortly, and say, you know, this is where you should put your money because this will help you in this regard. It helps with crime too, which is a big interest of the mayor in Baltimore. And it's also going to help with water quality. So I really think that's not 3, but to me that's a really big one. And I think that the other thing that we need to really think about is how we're going to support and train students who can think in this very transdisciplinary mode. And certainly what you guys are doing here, I think, is a wonderful step in that direction. I loved what we were able to do over the last 2 days. My husband's an architect, and you know, he's talks about doing charrettes as an architect, where they would kind of solve a problem in a short amount of time. And that's kind of the model that I was playing with the students. So if we can think about more innovative ways of helping our students to get their feet wet early, I think in the long run they're going to be better students. And then I think in general, and this is really meta, but we have to think about our higher education system. So my graduate students coming in oftentimes are coming with $100,000 worth of debt. They're coming in with a mortgage to be a graduate student. And so that's my small soapbox on that is, and I'm from higher education, I love my job. But you know, there's something about making our undergraduate education more affordable that seems very important right now.
Great. Well, thank you, Dr. Harris. It seems like the questions in the room keep increasing, but unfortunately we're going to have to wrap up. I think, will you be willing to stay
I'm
around
happy
for a
to
little
stay
bit
and
longer
talk.
to answer additional questions? Thank you all for coming again tonight, and again, please come back to hear the students' capstone presentation on a similar topic next month, December 13th at 2 p.m. Thank you. Thank you.
All right. Yeah.